Well, thank you, Oscar, and thank you for all the Jump Dev organizers to give me this great opportunity to tell you some of the things I'm interested in, and for organizing the day of super interesting talks in general. And so today I'll talk about optimization solvers in JuliaSmoothOptimizers, which is also a GitHub organization, which is sort of complementary to what Jump is doing. Except that we are really focused on developing solvers. Okay. So this is joint work with Dominique Orban, Abel Siqueira, and others. I'll tell you about. Oh yeah, thanks. In a few slides. Okay, some preliminaries. So in general, I'm interested in nonlinear, non-convex optimization, meaning you want to minimize or maximize some function. You have constraints that are described by inequalities and bounds. And the algorithms I'm studying are always based on computing derivatives, so I will assume that everything is smooth. And if I tell you that I'm solving something, it's usually trying to find a local minima or satisfying some stationary conditions. Okay, so nothing too surprising for you, I'm pretty sure. And to tell you a few more words about JuliaSmoothOptimizers, our scientific background is numerical linear algebra and optimization. So I told you already, it's a GitHub organization, and that was first initiated in 2015 by Dominique Orban and Abel Siqueira. And the first packages were CUTEst.jl, AmpleNLReader.jl, Krylov.jl. And the core contributors of the organizations are researchers in these two fields of numerical linear algebra and optimization. Okay, and so in particular, that means that we want to write research paper, studying algorithms, playing with them, and also studying. Okay, so everything that I'm presenting to you today, we also use that with students. We ask students to write solvers, make benchmarks, and everything like that. Okay. Awesome. I think my talk is also a good follow-up of last year talk about JuliaSmoothOptimizers by Dominique Orban. I'll let you review that if you want. And now we have a new fancy website called JSO.dev. Okay. So since JuliaSmoothOptimizers, it's like too long for me to repeat 100 times during this talk, I'll just say JSO. Awesome, and so since 2019, to give a few words, there has been 21 journal accepted publications and a book about JSO packages or using JSO packages. And it's now about 50 Julia packages plus a dozen not registered packages. So it's starting to be really crazy to maintain. And in my talk, I will only talk about the smooth nonlinear optimization part. So nothing about linear algebra, and also there are some new packages on non-smooth optimization. So awesome, and to give you like a slightly outdated table with all the packages classified in category, here it is. So you'll see there are packages about modeling problems, solvers, wrappers with existing solvers, linear algebra, and some other really nice things, like we have a lot of test problems packages and some various tools. We are really dedicated to make the packages as good as possible. So we have a lot of things for unit testings, test problems, and so on and so forth. Cool. So some motivations about my talk. So JSO has become a very large organization with multiple options for each covered problems, meaning for each problem now we're starting to have several algorithms. And it might take some time to find the right modeling tool and the right solver. Like if you don't know anything about JSO, like you would have to find what's the right package for your solver and everything and so on. So we needed, I think, a tool that gives a simple and intuitive entry point to the JSO universe. And also that tool would have to be sufficiently nice to easily prototype and compare solvers to find the right option. Okay, And I believe the answer to all these observations is what's called JSOSuite.jl. So the package's registration is ongoing, so the name might change a bit, but the spirit will stay. Okay. Cool. So I know you like codes. I don't know if black was the right color for the background, but you should manage to see it a bit. So essentially what we would like to do is just ask the user to give us a function, an initial guess, and then say, oh, I want to minimize this, and bam, okay? Or maybe the user actually wants to do all this in single precision in float32, and then he will give us a float32 vector as initial guess, and I want to do everything in float32, okay? And the same with constraints. So the rest of my talk will be a bit to explain what's behind all that. Okay, and so first part in this is that you have to modelize the problem and then you have to solve the problem. So I'll talk about the modelization part first. And the specificity of JuliaSmoothOptimizers is all in one of our core package, which is NLPModels.jl, which provides a standardized API for general nonlinear non-convex optimization problem of this form, okay? So you give me an objective function, and then you give me a constraint function to describe your constraints and eventually bounds, okay? And what NLPModels.jl does is that it provides a list of methods that you can rely on to access this problem. So typically things that we want to evaluate the objective function, but also compute its derivatives, do the same for the constraints, and maybe you don't want to have the Hessian matrix, but just want to do Hessian vector products, and so on and so forth, okay? So a small add-on this is that you can also actually define separately linear and nonlinear constraints, which can be convenient sometimes, okay? Cool, so as I said, essentially you want to access derivatives, and we see it as two ways. Either you want to compute factorizations of some system involving these matrices so that you can access the Jacobian and Hessian as sparse matrices in CO structure, or maybe you want to derive a factorization-free method and then just want to access a matrix vector product, okay? So you can do this either by accessing the hprod or jprod function, or you can ask the NLP model to give you some lazy matrix structure via linear operators, okay? Awesome, and so actually NLPModels.jl does not do anything but describing these abstract functions. Then you have to implement them as some concrete model. So I'm sure for all of you, the intuitive way would be to build a jump model, and then you would call NLP model jump to just squeeze the jump model as in the NLP model API. So that works really well. But you can also do other things, like we have one package called ADNLPModel. I will tell you more about this one in a moment, that use automatic differentiation. You could give us the function by hand with manual NLP model. And why we need this NLP model is also to adapt to some specific situations where you know more about the problems. And that's why we have, for instance, PDNLPModel.jl when designed for PD constraint optimization, and maybe you have a finite element discretization of your PDE, and you want to use that to access the derivative and build your discretized PD constraint model, and so PDNLP model will do that, okay? And same thing would happen for other examples. Here I noted partially separable NLP models and other wrappers with machine learning systems, okay? Cool, so a few things I won't talk about, at least not for a long time, is that you can also specify your problem, for instance, here with nonlinear least squares, where your objective function is actually the square norm of some residual function, and maybe you know that some algorithms specified for this, such as Gauss-Newton or Levenberg-Marquardt algorithms, they will want to rely not on the Hessian matrix of this objective function, but just on the residual and the derivative of the residual, okay? So that we extend the abstract NLPModel API to this case so that you can also access the derivative of this, and then your algorithm can access this, okay? Another really interesting thing with NLP model is that you can also very easily transform your problem. In case you have read some research paper about algorithms, very often they tell you, oh, we can solve inequality, but first you have to write the problem with slack variables. And then you start to think, oh, wow, I'll have to rewrite the whole thing. And with NLP model, then it's just a one-liner thing, okay? So we, in the package NLP model modifiers, we have a set of transformations like this that does everything for you. Cool, so that's sort of a brief overview of some of the capabilities of NLP model, and I want to say a few more words about ADNLP model. So the AD stands for automatic differentiation, and that's a great one because it doesn't ask much. The user can provide a Julia function, and that's it, okay? So the great part about this is that you can use any floating point type that support arithmetic operations. And essentially we use as base forward diff and reverse diff to compute derivatives, okay? And so actually that's just the default. We also provide derivatives with other packages. I'll give you an example next slide, okay? And so the package was designed with a backend organization of the different functions where we need automatic differentiation. So it's super easy actually to build one model and compare two AD system and switch AD system and so on and so forth, okay? And one of the recent add that was, I think, really important is also to add sparse Jacobian and sparse Hessian computation. Cool. So yeah, to give you a slightly more concrete example, so here I would define an ADNLP model and not the exclamation mark. It's because I'm specifying here that the constraint function will be an in-place function. That's usually very useful to save allocations later on. And so that's pretty intuitive. I think you would have to give the objective function, the initial guess, the constraint function, bounds for the constraints. And then that's what I said with the backend system. So in the NLP model API, you have a set of operations. And here for the gradient, I will want to use enzyme to compute the gradient, forward diff to compute Jacobian vector product, and reverse diff to do the transpose Jacobian vector product, for instance. Okay, and if you want to compare then Jacobian transpose vector product here, you could just switch the backend, okay, as easy as that. And so we also define some shortcut, so it's in green, maybe you don't see it, but just instead of specifying all the operations, you can just say, okay, let's do the optimized backend or the default backend. Awesome, and then another really nice companion package for ADNLP model, and I think it's also interesting for JUMP, is a package called OptimizationProblems.jl that contains a list of close to 400 problems in JUMP and in ADNLP model format, okay? So we use this one to do a lot of benchmarks, and the package also provides a meta in a data frame that gives you all the informations regarding the problems that are there, so that's good to select problems beforehand without having to load them. And if some problems are non-linearly squares, then you can ask for an ADNLS model instead of the ADNLP model, so then you could access the residual directly if you have an NLS solver. And among these 400 problems, about 100 are scalable, meaning that depending on some parameter, you can sort of choose the number of variables and the number of constraints. Okay. And if you are interested in contributing to this, we maintain list of issues with problems that we are planning to implement, or you can add the ones you are interested in. Cool, and then we could derive stuff like this. So this is one benchmark among many others that we could do. It's it can be useful, and it will be no surprise that usually jump is doing really good. And then you can see differences when you use reverse diff for the gradient compared to forward diff to the gradient, which is no big surprise, I think. Okay, and then you could derive this for more problems. So that's on 95 problems from OptimizationProblems.jl, where you can change the number of variables. Okay, cool. And another really interesting features, and actually that's one of my strong motivations in ADNLP model, is the possibility to create mixed NLP models. So let's say you have some very nice application with some structures, and maybe you know the Jacobian matrix, maybe you know the Hessian matrix, but don't want to compute optimized Jacobian vector product, Hessian vector product, for instance. And that was my case in ADNLPModels.jl. I know how to compute the Jacobian, but then to compute Jacobian vector product, I had to reevaluate the whole Jacobian, and that was painful and not that useful for my case. And so instead of my backend, I can, instead of giving a backend to compute the derivative, I can actually give as a backend an other NLP model. And then instead of using automatic differentiation for this backend, it will use the existing model. Okay. So then with the construction I'm showing here, so the model on line 2 is importing one of the PD constraint optimization problems that are defined in this package. And then, okay, so that's just a bit of rewriting of the objective and the constraints. And then most important is on line 13 and 14 that I'm saying, oh, Jacobian backend, actually you can take the original NLP model. Okay. And so the resulting NLP will have optimized matrix vector product with automatic differentiation, but will keep what I know from the problem. Okay, so I think it's pretty cool. Great. So that explains most of it for the modeling part and some of the progress with ADNLP model. And so now what you will ask is how we solve this problem. And in JuliaSmoothOptimizers we have something we called JSO-compliant solver. So it's a set of rules, and if you satisfy those rules, you have a JSO-compliant solvers, and actually there are only 2 rules. You need to accept an abstract NLP model as input, and you have to return a generic execution stat. So that's just some structure we define with some basic results from your optimization. Okay. And that's it. And what I think is really great is that then the solvers you defined, they rely on the NLPModel API, but they don't have to know anything about the model. Okay. So if you have a PD constraint optimization, or if you have some nonlinear least square, they can they all implement the NLPModel API, and you can use the same solver. And so as I said, the list of packages on solvers is growing. We have wrappers to existing solvers from Knitro Ipopt via actually the jump Ipopt.jl and Knitro.jl. We have also wrappers to AlgenCan thanks to Paulo Silva, and some homemade Julia implementations. So here I'm mentioning a RipQP, which is an interior point methods for quadratic programs, and then some solvers for nonlinear optimization like Percival.jl, which is an augmented Lagrangian method, and DCISolver, FletcherPenaltySolver for equality constraints right now, but this will be extended soon, I hope. Awesome. And so to talk slightly more about JSOSuite, so back to this very generic package. So JSOSuite will first define a data frame with most of the information you would like about the different solvers. So here I just truncated the columns. You have like 14 of them. And so these are the 13 solvers that we have in JSOSuite. And you would have some name, the name of the package, and other columns would tell you if it uses second order derivative, if it's compatible with bounds, and so on and so forth. Okay? So that you don't have to know anything about the solvers to start exploring what are their capabilities. And then JSOSuite first method will select optimizers, so that you would define your NLP model, and then pass your NLP model to select optimizers, and it will start to analyze it. Like basic things would be, okay, first determine if the solvers that are adapted to your problem, is it unconstrained, is it bound constrained, does it have equality constraint, and so on and so forth. And then check if it's nonlinear, check if it can use second order derivative or only first order derivatives, and then gives you a list of the available solvers. Okay, and then you can just call the solve or minimize here and solve the problem. Okay. So that's pretty cool. And so at the same time, we are trying to maintain a list of keywords arguments that are common to all the solvers. Okay, so that we will do the conversion in stopping criteria for you, which is I think good. Great, and one slide I'm particularly proud to show you, and as usual, sometimes a lot of work is summed up in 8 lines of code. So you can also use an in-place solve for your solvers. And that's particularly useful when you have a loop, for instance, and you want to solve again and again the same problem. You don't want to reallocate memory, you want to reuse the same memory. And so we have the solve exclamation mark. And what I'm trying to show you on this slide is actually, so I'm solving some problem with Percival, and we are saying that resolving the problem doesn't allocate anything. Okay. So actually, you see on line 2, I'm defining an NLP from NLP model test. So this package contains, in particular, a list of problems where accessing the model doesn't allocate anything. Okay. And so here I'm really testing what the solver does. And so the solver structure contains all the memory that you will use during the iterations of the algorithm. And stat is the structure I told you about that store the results. And so calling solve should do the trick. Okay. And I think that's kind of impressive because Percival, it's an augmented Lagrangian method. So it iteratively solved unconstrained or bound constrained problems. So these solvers are also allocation free in this sense. And these solvers called Krylov methods also that are also allocation free in this sense. Okay. So a lot of solvers satisfy this. Cool. And so that's essentially all you have to know to use JSO. The last bit, since we are researchers and we want to write papers, study algorithms, compare algorithms, is to do benchmarking. I'm just giving you a list, link to some benchmarks where you could see, and believe me that it's just like 10 or 50 lines to do a benchmarking to generate performance profile. And I thought I'd give you one example. So here I took problems from the collection of problem CUTEst. I've selected equality constraint problem, so there are no bounds, just equality constraints with up to 10,000 variables and 10,000 constraints. So that gave me 82 problems. And I tried to compare here Ipopt, Knitro, and DCISolver, one of our homemade solvers. And so DCI is in green, and it's doing, I think, quite well. Comparing that Knitro and Ipopt have been there for decades almost now, and are well-studied solvers and well-optimized solvers. And actually, I think the figure on the right actually shows that we have some margin in probably parameters of the solvers to avoid doing unnecessary stuff. Okay, so these are the Dolan and Murray performance benchmark performance profile. Cool, and so I can go on and on. This would be another benchmark. Here I'm comparing unconstrained solvers on 80 problems from OptimizationProblems.jl, and the computations were done in float 32, for instance. So you see that the number of problems solved is a bit smaller because, again, probably parameters were not optimized for the single precision. And yeah, and one last benchmark that one of the students in our team in Montreal sent me, Geoffroy Lecomte, who is a PhD student and developer of RipQP. So this is the kind of algorithms we are also super interested in. it's what we call multi-precision solvers or mixed precision solvers, so that first it does the first iteration in float 32, and then when it judges that it's useful, it switches to float 64, okay? And so the line in red would be this multi-precision strategy, and the line in blue would be just using float 64 all the time, okay? And that's the kind of progress we are hoping to get. And as you see, what's funny is that the float 64 only version solves more problem, because switching precision always comes with some risks. Okay, so some work still to be done there. Awesome. So to conclude this presentation, I wanted to emphasize that JuliaSmoothOptimizers NLPModels API was first designed to solvers, and now we have a list of so many solvers that are great, I think, but it's really difficult to access. And so JSOSuite was the solution to bring JSO optimization facilities to the rest of the world, essentially. Okay, and I believe it's becoming a real good tool to prototype and choose the most adequate optimization solvers. So it's at a pretty early stage right now, but the goal is to make it a sort of a pedagogical tool. Okay. So what we are learning in a numerical optimization class, that you have to use this solver in this case, and so on and so forth, like JSOSuite would do the trick, okay? Awesome. So thank you very much for your attention, and I'm really happy to answer questions.
So we have time for a couple of questions.
Just reset the question.
When you showed that automatic differentiation package, you had special support for in-place functions, and I guess you just exploit that in the backend. Then forward diff offered if you use that. Do you have some benchmarks on that? Comparing in and out of place differentiation, because there's an open issue in abstract differentiation where they are asking for those kinds of benchmarks.
So you mean our benchmarks between using in-place and out-of-place functions? Okay, so the question was, do we have benchmarks comparing in-place and out-of-place functions in automatic differentiation? And the answer is pretty simple. I don't have benchmark, but I noticed from the very start that it's a lot slower using out-of-place functions, because I think we learn all by coding in Julia that having to allocate things is slowing down essentially the code. So, however, it's a lot more painful to do automatic differentiation with in-place functions. So it was a lot more work. And if we were to do benchmark with Zygot, for instance, usually Zygot is, on the type of figure I showed, usually Zygot is a lot slower because of this kind of things.
Thanks very much.
Thank you.